But I again say, just because to write an equation, I can write the equation for the noise power. It is k by 1 plus f by fc the whole square into delta f. So you can never say the popcorn noise will always vary in this fashion. It is just an empirical formula just to relate mathematically how the popcorn noise is going to have a frequency dependent behavior. Again, you see it is 1 by f square. F is coming the denominator, it is having a power of 2. So high frequency operation will completely reduce your popcorn noise. So that is one advantage you have when you go for wireless communication where you work with megahertz and gigahertz. This popcorn noise will almost become negligible. And here also K is an empirical device parameter, and it is depends on the fabrication methodology. And F is a corner frequency below which the burst noise flattens out. Flattens out means it becomes constant. So for frequency above Fc, you have to use this formula, K Fc square into 1 by Fl minus 1 by Fh. So below Fc, what they say, below Fc, the noise is flattening. Flattening means it is going to be constant. It is not going to have much of a variation. And Fc is called as corner frequency. Just to find bandwidth, we define the frequency FL and FH, where between FL and FH, we say the power is maximum, or it is a minimum 50%, it is maximum 100%. Same way, we define a frequency FC called as corner frequency in popcorn noise. What is the definition for corner frequency? Corner frequency is the frequency below which the noise is constant, flattens out. And above FC, if you want to calculate the popcorn noise, you have to replace the equation by this one, k fc square into 1 by fl minus 1 by fh. So this mathematical relation you have to understand for popcorn noise. And uh, one formula is less than fc, I use this formula, and second formula, I use this term into delta f. I replace this k by 1 plus f by fc square by k fc square into 1 by fl minus 1 by fh into delta f. And FL and FH, are the two corner frequencies of your uh, device, high upper cutoff frequency and lower cutoff frequency. So these two frequencies have nothing to do with FC. FC is the frequency below which the noise is constant, above which the noise is going to vary predominantly. So we write the equation for the noise above FC in terms of FC, FL, and FH. So that is what we have about popcorn noise. Nothing much because it is purely dependent on fabrication. And if you follow a very stringent mechanism for cleansing your devices, then this popcorn noise can be ensured to have a minimal RMS noise power. So that is what we have for the four types of noises in semiconductors. We have seen thermal noise, Johnson noise, flicker noise, and popcorn noise. So you have to remember how these noises are produced in devices and MOSFET specifically, and remember the current equation. If not the exact equation, you can remember, at least remember how the current or voltage varies inversely or directly proportional to K. Like that, at least remember logically, so that when you write your answers, you can present it that way. Of course, it is difficult to remember all these equations with all the units and other stuff. At least you can remember if it is flicker noise in junction, it is going to depend on, it is proportional to K, it is proportional to I, it is inversely proportional to F, it is inversely proportional to AJ. So like that, you can logically remember the equation so that you can understand how the noises are going to vary with respect to frequencies. So any doubts so far in all the types of noises what we have seen, you can ask any queries if you have.